Okay, we're going to continue talking about stars now. We're not going to be talking about the sun per se. We're going to talk about other stars. It's funny, I don't know if you guys ever read FML, but it's funny, one person talking about, my teacher was trying to say that, stars are like the sun. What an idiot. Yeah. The sun is a star. Don't, just believe me on this one. The sun is a star. Something that I think may have mentioned happened my first year teaching at Pacific Union College. So back, I was like 27. That was a long time ago, by the way. We're on a trip, and a student who was taking astronomy class was pointing out different stars and saying, and they're all just reflecting the sunlight. What reflects sunlight? Louder so I can hear it. Okay, the moon does. The other things we see in the sky that are reflecting sunlight are called planets. Right? The planets and the moon reflect sunlight. The stars actually produce light because the sun is a star, produces light. Why does the sun produce light? Most fundamental reason. Why does it produce light? Fusion. Okay, that's not the most fundamental. It's a true reason. It has fusion in its core, producing heat. And it's because it's hot. That's what I was looking for, the most fundamental. Just because it's hot, it gives off light. So we're going to look at other stars. This picture here is one we'll see later that shows the spectra of light coming from a variety of different stars. And we'll learn that this is actually broken down to separate the stars by their temperatures and the light they give off. What was your question, Max?
Yeah, I was just thinking about the proton chain.
Yes.
And wondering where the helium-4 goes.
Where the helium-4 goes?
Yeah. Because you talk about how there's a whole bunch of helium-4 being created, what happens to it?
Okay. The helium-4, so you take basically, for the net reaction, 4 protons, 4 hydrogen, become a helium. It's all just nuclei, right? The electrons are free. Try to be like the song. So what happens is that helium is essentially the ash. We use combustion terms. So when the fusion is occurring, we say it's burning hydrogen, even though it's not really burning anything. And we say the ash is the helium. It's the waste product. And that helium is basically just being compressed in the core. And when the core runs out of hydrogen, when hydrogen runs low so that the core can't efficiently produce fusion of hydrogen, then we're going to get to the death of stars, but we're going to have, the core will start collapsing because you don't have as much outward explosion. And it'll get hot enough outside of the core for hydrogen that's outside of the core, right? The core will be pretty much all helium then, because it'll just, most dense stuff, so stay in the center. And then you'll have a shell of hydrogen fusion that occurs outside of the core. And as that starts going outward, it's going to, of course, dump more helium in the center. The pressure and temperature in the center will go up until the helium actually will start fusing. We'll have what we call the triple alpha process, where helium will fuse into carbon. You have 3 helium have to fuse essentially all at the same time to produce carbon. And so the sun will then produce carbon. It'll fuse some carbon with helium to produce oxygen, and that'll be the end of it. So then it will become a white dwarf, carbon oxygen white dwarf. Yes?
So what's harder, a larger sun or a smaller sun? So a dwarf sun or a...
The basic rule is the bigger the star, the hotter it is. There are exceptions to that. If it's a main sequence star, that's a truism. If it's a giant, giants are a stage of death, and the giants tend to be cooler because they've expanded.
The binary stars kind of switch
there are some situations where that occurs, but not in general. Now that everyone's here, let's talk about A, voting tomorrow, and B, lab tomorrow. Is anyone actually voting here in Lincoln? Okay, so for those 2 of you, there is something that I think everybody needs to know if they haven't looked at the ballot. The state of Nebraska repealed the death sentence a few years back. And now that repeal is up for repeal. So you have a vote to retain or repeal. And if you repeal, you're repealing the repeal. If you retain, you're retaining the repeal. Confusing, right? I swear no matter which way this goes, the side that loses is just going to go, sue and say, voters didn't understand. Bottom line is, if you vote to retain, that means you're voting to keep the repeal on the death sentence. So retain means no death sentence. Repeal means you're repealing the repeal, which will return the death sentence. That's just a confusing issue. Another one that I think is important, and everyone should be aware of what a bond issue is. When I was younger in California, it was required on every ballot there is a tax statement that says what this will do to your taxes. And so they just started making everything a bond act, and they said this has no direct effect on your taxes. But what a bond act is doing is it's selling bonds that are then going to be repaid by government funds. And where does that come from? From taxes. So we have a bond issue for, I think it's 369 million or something in that ballpark. And the plan is to put that on the property taxes. Before this year, we paid just a little over 2%, but the mayor proposed a budget that was rejected by the city council. They proposed their own. The mayor rejected theirs, and they have to have 100% to not go with the mayor's. They had one person that was holdout. And so there was actually a legal battle, but they now have a mandate to raise our property taxes to somewhere in the ballpark of 2.3%, which means, we're paying a large amount of property tax every year. And this would just increase that property tax. So think about that. If you think that, it's worth it, don't just say, like California voters, oh, no taxes, free money. That's not what it is. And of course, it's probably your first chance to vote in a presidential election. So, think seriously about that. Vote for the person who you think best represents you, not who best represents your friend or who is opposed to the most heinous person in the world.
It was nice knowing you. When we get shipped back to Mexico, even though I was born from Massachusetts, they have no Hispanic descent at all.
For lab tomorrow night, if it's clear, I hope to go out to Gary Walter's house. We'll meet here no matter what. Don't just head out there. Don't be late. We'll need to, if it's clear, we'll need to have some organized transportation. So I have my car, and I can take like 3 other people comfortably. How many can you take, Daniel?
6.
Counting yourself?
7.
Okay, so 6 plus you?
Yeah.
So that would only leave 2 more people. Somebody else have a car they'd be willing to offer. They could take themselves and one other? Okay, Yari. So just make sure that if it's clear, just go ahead and bring your car. You can always park back here. No problems with tickets or anything. Unless Daniel decides to, go on warpath.
I'd like to.
Okay, so we got those out of the way. Let's talk about star classifications. Now, we ended last class period talking about the parallax, and I decided I wanted to go through the math on this just real quickly. So if we look at this picture here is showing how we make the measurement. We actually, when the Earth is over here, we'll take a siding, perfect line. I'm going to use the straight line tool because I can at least make it hit. We'll take a siding to a star, and then we'll wait till we're on the other side of the sun and take another siding. And so the truth is, we have an angle that is this big, but the angle that's considered the parallax angle, which is for a very simple reason, is just half of that. So just that angle is the angle P. And so we have the baseline for that angle P is 1 astronomical unit. And now we're going to take this picture and look at it from a different perspective. We're going to look at it from the perspective of the star. So from the perspective of the star, here's that parallax angle P. Here's that distance of 1 astronomical unit. And so a really simple relationship here, the angle multiplied by the radius is equal to what we call the arc length S. So the arc length in this picture, the radius is the distance between the star and the sun. So in the picture, D is the radius distance between the star and the sun. And that 1 astronomical unit is the arc length S. And so we have a relationship here. Oh, and finally, I guess I should say this angle P is the angle theta. So we have a relationship that allows us to calculate P times the distance away is equal to the arc length of 1 astronomical unit. And so if we take this equation, we could solve it right away and say the distance is equal to 1 astronomical unit divided by P. The only thing that's missing between this and our actual equation we use is a unit conversion. Because if you're going to use that equation that the angle times the radius is equal to arc length, the angle has to be measured in units of radians. But if you remember, we called it a parsec because it was a parallax arc second. The angle is measured in arc seconds. So we have to do a conversion. 1 circle is equal to 2 pi radians, or 360 degrees. But 1 degree, so I'm going to use the degree sign, is equal to 60 arc minutes, and 1 arc minute is equal to 60 arc seconds. And so we have to go through our conversions to convert from a radian into an arc second. So I have 2 pi radians is equal to 360 degrees times 60 minutes per degree times 60 seconds per minute. To get rid of the 2 pi, divide both sides by 2 pi. And now I'm actually going to whip out my handy-dandy calculator. Actually, that's not the way I wanted to do it. I wanted to go the other way. I wanted to calculate what 1 arc second is equal to. Actually, no, that is what I was right. Remember, don't doubt yourself unless you really are wrong. Did you have a question? No, that was stretch. Okay. So just multiply this through 360 times 60 times 60 divided by 2 divided by pi. I bet you this has a pi button. Yeah, 3.1415925 will be enough digits. And that gives me, I know you guys can all read this, right? So 1 radian is 206.264.8065. Between friends, we just write this as 206.265 arc seconds. And so for our equation right here, if we want to put the parallax angle in arc seconds instead of radians, I have my final equation is D is equal to 1 astronomical unit over the parsec, or the parallax angle, times 206.265. Yeah. Okay, so it's 206,265 astronomical units times get my units right. I swear I've got something written funny in my units, but times arc seconds. And so that's the actual equation. So we just take that 206,265 astronomical units, and we define that as 1 parsec. So the definition of what a parsec is just that number that came from the unit conversion. And then we usually don't write that arc seconds out here in the end, and we simply say that the distance is 1 parsec divided by the parallax angle if the parallax angle is in arc seconds. So in reality, there really is a times 1 arc second there, so the units are going to cancel.
The parsec is a measurement, so it's like.
Right, so a parsec is defined as 1 parsec is equal to 206,265 astronomical units.
So what you're saying is Star Wars makes no sense when Han Solo says he did the what's called running in.
That is very correct. It makes no sense at all. People who defend Star Wars will try to say, well, really, it was about the whole length contraction because the distance between 2 points depends on how fast you travel. If you travel fast, you have what we call length contraction. And so they said the trick was he actually traveled a shorter distance because he was going so fast. It's really stupid.
So basically, it would have made sense if you said he was going like 12 parsecs per hour.
Well, if he said I was flying at a speed of this many parsecs per hour, that would have made sense.
Yeah.
Or if he would have said it took me this long and used time. But see, the problem is the people who make science fiction don't necessarily know their science, and they just thought that that was a unit of time.
Yay.
Yeah. Okay, so I just wanted you to see where this comes from, just to make it a little less magic equation and more, yeah, that's reasonable. You're just taking the relationship between angle and arc length. I usually go one step between writing that equation, theta r is equal to s, and say that the circumference is equal to 2 pi times the radius. Everybody knows that, right? But 2 pi is the angle for a complete circle. So that 2 pi was really theta for a complete circle. And so that equation is equivalent in meaning to this one. All right, let's move on. Here's some pictures. Anybody recognize this thing? Okay, Big Dipper. How would you know if it's the Big Dipper versus the Little Dipper? The middle one is the one that's essentially what it looks like now, by the way. How would you know the difference? Yeah. The handle bends, curves the opposite direction for the Little Dipper versus the Big Dipper. The Big Dipper, you have the cup, and then the handle goes like this. The Little Dipper, the handle goes like this. So that would be the Big Dipper, because starting tomorrow, you could do the lab final. Let's practice the names of these stars. Not part of today's material, but we can do it. So what's the name of the last star out here at the end? Alkaid. This only shows one star, so that's going to be the bright one. What's the name of the bright one there? I see one person has been preparing. What about our next star?
Isn't there a star right on top of my guy?
There is. I'm going to come back to it. What about the next one that's shown here?
Starts with an A.
Starts with an A. That's right. Okay, Alkaid, Mizar, Alioth, or
We got an M again.
okay. Next, Vector Fad. Two more. Go ahead. What letters to start with, Aldwin?
What is it, B? I don't remember. Oh, it's an A. N. It's an N.
Nailed it.
URSTUV.
Mirac, and the last one? Doobie. I just realized that wasn't a 6 that I put there. Okay, now, it was pointed out that there's another star right here that's a much smaller star. It kind of messes with our AM, PMD sequence. That's Alcor. Right. So that's 8 stars that I expect pretty much everyone will have learned. It just makes it really easy if you just learn those. Whip them out. Polaris. If you're going to use Doobie as a red giant, you're going to have another red giant and one more, and Lyra.
Use Mirac and Doobie to find the North Star.
Yes, that's right. Now, what was the point of these pictures? It wasn't to name them. It was that the positions of the stars are not fixed. The stars are moving. It should be no surprise that the stars are moving, but what is surprising is that we don't see it. We don't see it for a very simple reason. We're a long distance away. I like to go to Yosemite National Park and go up to Glacier Point and you look down the valley and those cars appear to be moving so slowly. You get down there and you're like, well, they're moving 40 miles an hour. Why were they going so slow when I was up there? They were still going 40 miles an hour, but they're so far away. I was just measuring how the angle was changing with time. And the farther away it is, the smaller the angle is going to be for the same distance it traveled. And so since these stars are really, really far away, even though they're really, really moving fast compared to us, their angles change by so small amount that we don't really notice. Now, astronomers do notice, and they try to measure these. They call it the proper motion, the actual change in angular position seen by the stars. And so when we go out and we look for the positions of stars, everything has a right ascension and a declination. But we have the epochs that they use. And I think every 10 years they put in a new epoch that has slightly changed coordinates because of these proper motions because the stars are moving. So over the course of 10 years, it might change by 1,000th of a degree. Not a big shift, but when you're using a telescope, it's actually enough to make so it doesn't aim right anymore. So they really do move, and if you wait thousands of years, you'll see enough motion to see, yeah, I can tell that those are the same thing, especially because they drew the lines on for me. But it doesn't really look the same because the stars have moved relative to each other. So when they talk about the motion of the stars, you have two pieces. The radial velocity, what we can measure with the Doppler shift of it coming toward or away from us. And then we have its proper motion, its motion that we would actually be able to see. It's also called the tangential velocity. That's actually all I'm going to talk about, the positions of the stars here. These two words are important to distinguish. In fact, our first clicker question is distinguishing between these two words, luminosity and brightness. Luminosity is how much light an object gives off. There's another word for intensity. But the luminosity is how much light it gives off. So if you have a 65-watt light bulb and a 120-watt light bulb, which one's going to give off more light? You guys not down with light bulbs?
I just didn't hear what the numbers were.
65 and 120. Okay, the 120 watts gives off more. The watt is actually the unit for the intensity. That's energy per second. And so luminosity, since it's really the same thing as intensity, is measuring the energy per second that comes off of the star. So luminosity, how much light it gives off. Brightness is how much light we receive per unit of area. So it's actually measured in units of intensity per meter squared. But it's what we perceive. So now we established the 120-watt light bulb is brighter, more luminous than the 65-watt light bulb. But if I have a 120-watt light bulb and it's over at College View Academy, if we open that line, and I have a 65 watt light bulb and it's sitting right here in front of the Latifah, which one's going to look brighter to me? The 65 watt one. It's not putting off as much light, but because it's so much closer, it would appear brighter. So the brightness has to do with where you are. It's how bright it is to you. Something could be a different position and the brightnesses would be different. Whereas the luminosity is how much light it's putting off. That's going to be the same for everybody. So when we talk about both of these terms, we need to be able to distinguish luminosity as a property of the object alone. Brightness depends on both the luminosity and the distance away. So, what are we going to do with them? Well, first we're going to answer a clicker question. Which is the correct statement about luminosity and brightness? Only one of these is a correct statement. I know, they're long enough. It's going to take you a while just to read them.
On my clicker finally.
Excellent. Channel 33.
Turns out it was in my bag the whole time.
Yeah, the whole time. Leo. We're going long distance today, too. Actually, let me shuffle them up a sec. It's been exactly a month since Latifah answered a question. Still waiting on Aldwin and Daniel. 33. Channel 33. You don't. Okay, everybody's in. All right. We had. This is going to be tough for you, Latifah. 11 people said B. What'd you say, Latifah?
I said B.
What was your reasoning?
Because you said luminosity is how much light it gives off, and brightness is how much light you receive, and it's based on perception and luminosity.
Okay. She added something in there besides just reading it because it is kind of hard when, because those are the definitions. It's hard to explain when they're just right. The others were wrong. That one was right. Okay, good job. The brightness depends on your position as well as the luminosity. This is how much you perceive. So how do those two relate? Well, the luminosity is the light that's coming out. And for stars, it's a really perfect approximation to say that the light is going out the same in all directions. When we get to other objects, it's not perfectly true. But for a star, it's pretty much going the same amount of light in all directions. And so we can say that the brightness is going to be how much luminosity, that's how much energy per second was coming off, divided by the area of a spherical shell that's the distance from the object to us. Now, the area of a sphere, most students don't know this, the area of a sphere is 4 pi times the radius squared. So this here is saying that the brightness is equal to the luminosity divided by the area of that sphere. And so 4 pi d squared, d is the radius of the sphere. I know it looks like diameter, doesn't it? But it stands for distance. That's why I'm using the form the textbook did. So that's the relationship between the two. So what happens if you get, as the picture shows, if you move 3 times farther away? The luminosity stays the same. What happens to the brightness if you go 3 times farther away? If D becomes 3D, what's that equation going to become? D prime is equal to 3D. L prime equals, and remember L is equal to, B prime equals, and B is equal to L over 4 pi D squared. So what would B prime be? The new brightness. Just the equation. Spit it out to me. What's in the numerator position?
If D is 3D,
Yes, if D becomes 3D.
well, how did he square it?
Well, let's start.
36 pi.
Here's my divisor. What's above the divisor? L, the luminosity. What's below? For what? 4 pi. And then I got to put parentheses, my new D, my D prime, squared.
Wait, why is D prime 3D?
It's because in the picture, it moved from being a distance D away to being a distance 3D away. Right? This versus this.
Wait, did you derive it?
Well, this is the entire derivation for the relationship between brightness and luminosity because the area, the brightness is the luminosity divided by the area of a sphere. And so area is 4 pi times the radius squared, and the D here stood for radius. So that is the entirety of the derivation. It's not a very drawn out one.
But if you were to derive the denominator, that would be 8 pi d.
It'd be what?
8 pi d, right? Are you not deriving the denominator? I'm sorry, I'm confused what you're deriving.
Well, this here is the derivation for the relationship between brightness and luminosity.
Okay.
And now we're saying, so what would here's going to be my B prime, the brightness out here, compared to my B, my brightness here.
Okay.
So now we're finding actual comparison of the brightnesses in two locations. And so our equation is going to be this equation. It's the same star, so the same luminosity. And of course, 4 and pi are constants. But D became 3D. And so everything else is the same here, but D became 3D. But then when I square that 3D, what do I have? I have 9D squared. Now, Max has been saying 36 for a long time because 9 times 4 is 36. But I am going to write it this way. Not that way, that way. Because this here is the initial brightness. And so it's 1/9 of the initial brightness. If I go 3 times the distance, it's 1/9 because 3 squared is 9. And so that's the thing I wanted to illustrate with this. If you double the distance, how would the brightness vary? 2 squared is 4. So if you double the distance, it would be 1/4 as bright. And of course, if you quadruple the distance, 4 squared is 16, it'd be 1/16 as bright, and so on. 10 times the distance, 100th. We can do the math. So that's how the brightness and luminosity mathematically relate. If there is a caveat. If there is nothing absorbing light between us and the star. There actually is gas in the universe, and so we have interstellar media that makes it so it's not perfect. This is the perfect case calculation. Now, given that relationship, I can take the same equation we just had, the equation that said the brightness is equal to the luminosity over 4 pi d squared, and I can just solve that for d. So that would be b 4 pi d squared equals L. Divide everything by b 4 pi. And I know this is the long way. D squared is equal to L over 4 pi b, square root both sides, and you have this relationship. That the distance to a star, if you know how bright it is and you know what its luminosity is, you can calculate its distance. Some stars, we call them, it's in red there, standard candles, are always the same brightness. Something like a type, type 2 supernova. I think that's what it is. It's always the same brightness, hence you know how bright it is, and you can determine its distance by measuring, or it's always the same luminosity. You measure its brightness, so you determine distance. Next question.
Does this equation work with all objects in the solar system? So theoretically, if like a TNO or a moon gave off enough, reflected enough light, we can measure its luminosity and brightness. We could find the distance.
Yes, this is true. This is true.
They
So
reflect very little light off.
this is actually a method that is used to estimate the sizes of distant objects like trans-Neptunian objects. It's actually the method they use. They measure how much light they get from it, they estimate its reflectivity, and then they go through some calculations to say, okay, so you have two things going on because if it's farther from the sun, it's getting less light. So it's a little more complicated to do the calculation, but that's what they're doing. And they assume a reflectivity of ice because they say they must all be pretty much ice. What's her name? Well, I don't remember the name of the person who came up with this, but we have it's actually going back to an ancient Greek. For some reason, I want to say Hipparchus again. I probably use his name too much. But an ancient Greek came up with a method to rate stars. He had the first magnitude stars, the ones that were really bright, right? That would be like your first magnitude star. Trying to think about who's the star of Hollywood. I don't even know. Well, let's talk football. A first magnitude star might be somebody like, Tom Brady.
Brady. Whoa.
What did you say?
I said Des Bryant.
Des Bryant? Defensive lineman?
Wide receiver.
Yeah, that's right. There is a wide receiver with that name too. I forgot. We had a defensive lineman on the Raiders and went to Chicago after us. Named Des Bryant. Okay, so Des Bryant. I don't know, maybe a magnitude 3 star. You go down so you get to, let's say, Blake Bortles, magnitude 6 star. Okay, so we have the magnitudes going from 1, the most important, to 6, the least important. And so it went through and just categorized by their brightness. And so that's useful. But of course, we being scientists, we want to actually be able to put some numbers to these with calculations and math equations. Makes us feel better about ourselves. We can use math equations. So what scientists have done is they've come up with a relationship. You see there in purple. If you have a difference of 5, so that's going from 1, the brightest, to 6, the dimmest, in the original calculations. That is a difference in brightness of 100 times. So a magnitude 1 star is 100 times brighter than a magnitude 6 star. And so then the scientist says, okay, now that we have this set, let's do some math. What kind of math equation can we make out of this? And so, okay, the equations are all shown over here. And the equations can be summarized. First, the ratio of the brightnesses is 100 raised to the difference divided by 5. So if the difference in the numbers was 5, such as going from a 1 to a 6, then you'd have 100 raised to the 1. The ratio would be 100. Now something that's important is to notice that it's brightness of 1 divided by brightness of 2 is equal to 100 raised to the lowercase m means what we call apparent magnitude, how bright it is, of 2 minus 1 over 5. That over 5 is a little annoying. And so they said, well, let's take 100 raised to the 1/5 power, and then we don't have to have the over 5. So 100 raised to the 1/5 power is 2.512. So the ratio of brightnesses is 2.512 raised to the difference in those apparent magnitudes. Now that was fun. That was good. What if we want to solve for M2 minus M1. Well, if I want to solve for M2 minus M1, the little math here, this is the hardest math gets in this entire class, by the way. I have this equation. I'm just going to come down below. Okay, first get my size right. I have this equation that says B1 over B2 is equal to 100 raised to the M2 minus M1 over 5. I can best deal with this by taking a log of both sides. So I'm going to do a log base 10 of both sides. And here's where the rules of logs are really cool. If I have a log of something raised to a power, I just bring the power out front. So that's going to be M2 minus M1 all over 5 times the log base 10 of 100. Log base 10 of 100. Do you know what a log means? There was one affirmative nod. That log means what power do I have to raise the base by to get to my answer? So if my answer is 100, it's basically asking me what power do I have to raise 10 to get 100? Well, 10 raised to what power is 100?
10. I mean, no. 2.
2. So that means that we know, just by knowing what a log is, that this here is just 2. So that means I have M2 minus M1 times 2 over 5, where I just brought the 5 over with the 2, is equal to log base 10 of B1 over B2. I wanted to solve for M2 minus M1, so now I just multiply both sides by 5 over 2. What's the easier way of writing 5 over 2? 2.5. So 2.5 times the log base 10 of B1 over B2 is equal to M2 minus M1. So if I know the brightnesses, I can put them into that equation and I can know the differences in the apparent magnitudes. So this equation that I have the black box around, it's really the same equation as this equation here, just solved for different variables. On the test, you'll just have both of them, so you can use them as you like. Now there's one last piece here, and I have to go back to the 2 preceding slides to get to that last piece. So we're going to come back and talk about this again. But I just wanted to show you how the math breaks down for these apparent magnitudes. Now once again, apparent magnitude, that's a measurement of how bright it is. Which ones were the brightest? What magnitude was the brightest? A 1. Which was the faintest? 6. Now this allows us to rate all stars, even ones that are too faint for us to see with the naked eye. So if I have a star that has an apparent magnitude of 12, that just means it's really, really faint. But we can measure with a telescope. We can measure how much brightness we receive from it, compare it to a star that we know what its brightness is, and we can calculate the difference, and we know, what the brightness is of that star. Or excuse me, the apparent magnitude of that star is. Now going back to this one here. Actually, I want to go to this one so we don't get distracted. This here is the Little Dipper. Notice the handle is the opposite direction of the arc. What stars do you see when you look at the Little Dipper? When we go outside in lab time, what stars do you see?
Polaris.
Okay, you see Polaris. What else? We've all looked at it. I pointed out it's hard to see. Basically, the only other things you see are these 2 stars. Now, when you look at the numbers, you can see why. 2 and 3 are brighter. 4 and 5 are dimmer. So those 4s and 5s are fairly faint. If it's dark out, you can see them. If you've got the moon, and it's going to be like a first quarter moon tomorrow, so we won't be able to see actual dark things as well as I would hope, but I want to get out there into the dark anyway. But if it's dark, you'd be able to see all of them. If it's bright out, like if you have a moon or if you have city lights, all you really see are those because they're the higher magnitude stars. It's actually easier to point out constellations when you do have some light because you don't see all of those distracting fainter stars. Okay, now for this slide. I've been talking everything about apparent magnitudes, which is measuring the brightness. But it would kind of be nice to have something that's relating the luminosity, the total amount of light that it gives off. And so what we have done, not me, Richard Webb, but we scientists in general, is said, well, let's make a standard of what's the apparent magnitude if you're 10 parsecs away from the star. And we're going to calculate what the apparent magnitude at a distance of 10 parsecs away is for every star. And so since the distance is the same, that measurement of brightness is actually going to tell me the luminosity of the star, because I have the same distance for all my comparisons. And so we call that the absolute magnitude. The absolute magnitude is the brightness measurement if you were 10 parsecs away. And so with that definition, the last equation here, well, those are, once again, the same equation just solved for different variables. We can take the distance an object is, distance between us and an object is d, and that reference distance of 10 parsecs, and the difference between the absolute and the apparent magnitudes is just equal to 5 times the log of the distance divided by 10 parsecs. So it's, if you know the distance away, you can determine the difference between the apparent magnitude and the absolute magnitude. Or if you know the absolute magnitude and the apparent magnitude, you can calculate the distance. So the lower equation there is just taking the same equation and solving it for distance. And I'm not going to do the math today to show you how you solve it for distance, but it's just a reverse of what we did before. So if we know what the apparent and absolute magnitudes are, we can determine the distance. So something that's important to know for nomenclature. Lowercase m is the apparent magnitude, which is essentially telling us about the brightness. Capital M is the absolute magnitude, which is essentially telling us about the luminosity. It's truly telling us about the brightness if you were 10 parsecs away. But because it's always 10 parsecs, when you compare the absolute magnitudes, you're comparing the luminosities, essentially. So make sure you can tell the difference in an uppercase and lowercase m. Now, finally, to the material on the left side. We've ignored this completely. This is just a table to show you how the actual brightness compares with apparent magnitudes. So if you have two objects that are the same magnitude, let's say a 1 and a 1, well, they're the same brightness. If they differ by 0.1, it's only a 10% difference in brightness. Not much difference at all. 0.5, 1 to a 1.5, that's a difference of 1.58, almost 60% brighter. Difference of 1, 2.512, to 6.31. You can see how it goes down until you get to 5. Difference of 5 is magnitude difference of 100. Difference of 10 is a magnitude difference of 10,000. Difference of 15 would have been a million. Difference of 20 would be 100 million. So you can use those numbers, right? If it's difference of 5, if it asks you how a 1 and a 6 relate, difference of 5, you should be able to just have in your head, oh, that's a difference of 100 times brightness. If it's not a difference of 5, then I go to either this equation here or this here, depending on which way it's asking me. Of course, if they told me it's a difference of 5, it would be the one up there. So that's the hardest math you're going to have to do. Make sure that I'll try to give you a homework problem, but that you have some practice doing it. So, if it comes up on a test, you don't go, can't do it. Okay, another clicker question. Star A has apparent magnitude of 5, while star B has apparent magnitude of 1. Which statement is true? All right, everybody's answered. And we have I can tell by your actions that my time is up. I wanted to have you discuss and then have Gabby explain it. Guess we'll go straight to Gabby.
Okay, so, well, the lower numbers are obviously have more light there. And so then you said that apparent magnitude was brightness while the absolute was luminosity, so I said D.
Okay, lower number is brighter, and because it's apparent, then you're dealing with the brightness rather than the luminosity. I'm not writing that down, and so you nailed it. All right, I'll see you for lab tomorrow. Remember, vote. I would say early and often, but
Have you voted already?